Now that we understand how light is being generated, we can now discuss the more relevant aspect of radiation, which is solar radiation. We want to focus on ultraviolet radiation coming from the sun. There's three different types of UV rays that matter to us on Earth. These are called UVA, B, and C, and you can see that UVC has the shortest wavelength, and then the UVA has the longest wavelength. Now again, going back to our discussion of wavelength and energy, you notice that this would have the highest energy, and then UVA would have the lowest energy, but all of them are quite harmful to us. Now, the shortest one of these, UVC, doesn't reach us very much because a lot of it is absorbed by other things. However, UVB and UVA do reach Earth, and we want to make sure that we are able to protect ourselves there. So what we want to talk about here is what is it that protects us from these harmful UV rays? A major portion of the atmosphere contains the molecule ozone. We have discussed ozone actually in a prior chapter when it was a pollutant in air. But ozone at the stratospheric level of the atmosphere is actually beneficial to humans because it helps protect from the radiation from these harmful UV rays. So specifically, the ozone layer in the stratosphere protects radiation with wavelengths between 242 to 320 nanometers, which really covers most of UVC and UVB, with a little bit of UVA being part of it. And then the oxygen that's also present in the outer atmosphere will cover most of the other UVC. Now, some of the UVA that's left over here at the bottom, then we have to figure out other ways to protect ourselves from it. So we talk about sunscreen and other things later on. But the higher energy ultraviolet radiation are these two right here, and they're blocked from reaching us on the surface of the Earth by both the ozone layer and the oxygen atmosphere. Before we can talk about how these two molecules actually protect us from these radiation, we first need to understand molecular structure, because that actually explains why these two molecules specifically are able to absorb the energy of this radiation. So to do that, we need to talk about something called Lewis structure, and that's a way for chemists to show how electrons and atoms are arranged in molecules. And the reason we care about this is because we want to be able to show how the chemical bonds in these molecules are able to absorb some of these light energy, preventing us from being exposed to these harmful radiation. First step of drawing Lewis structures rely on knowing the number of valence electrons in an atom. Valence electrons are electrons that are located on the outermost shell of an atom. So we talked about shells before, which is where the location of electrons are in an atom. So for example, if you have an atom that looks like this, and the electrons are illustrated as these little circles, the valence electron is the electron that is located the furthest away from the nucleus. So that red one is going to be your valence electron. So it's located on the outermost shell. Okay. The other electrons are what we call core electrons. The core electrons are not important in this particular discussion because what we care about here is electrons that could form chemical bonds, and only valence electrons will do that. You need to know how to count valence electrons when you're drawing Lewis structure. So the way to do that is simply by looking at the group number. So if you go back to the discussion about the periodic table early on, we had mentioned that there's 18 different groups in there, but another way of splitting the periodic table is by looking at the what we call main groups, which is 1 and 2, and then we go number 3 right here next to the transition metal and all the way to 8, and then the other 10 groups are right here, which are all transition metals. The reason splitting it this way helps us in Lewis structure drawing is because once we know which group number the element is found in using this splitting of the periodic table, that's exactly the same number of valence electron that that element will have. For example, if I have, sodium, which is right here, that's going to have 1 valence electron. If I have something like chlorine, which is right here, it's going to have 7 valence electrons. So knowing the location of the element in the periodic table and the group number automatically tells you how many valence electron that particular element has. Now, these valence electrons are important because they are the ones responsible for forming covalent bonds, forming other bonds. They're the ones that get transferred during chemical reaction. Valence electrons are pretty far away from the nucleus, so they don't experience as strong an attraction to the protons in the nucleus as as these core electrons do. Now, in covalent molecules, valence electrons are the ones that actually make up the covalent bond. Covalent bond is just a sharing of valence electrons between two atoms. So here's showing you how this whole thing works. So let's say you have atom A and atom B. Those are the nuclei of those atoms, and so there are protons in there, right? So the protons are attracted to electrons. So when the protons in here see the electron from the other atom, that electron is going to get pulled in due to that electrostatic attraction we've discussed a while ago. And then same thing here, the nucleus in atom B has protons. Those protons are going to be attracted to this electron here. So there is an incentive, therefore, for these two guys to come closer together to make a stronger interaction. When they come close enough, they form this bond. That bond, which is a sharing of those valence electrons, is what we call a covalent bond. And then the molecule, which is A and B, stuck together in that covalent bond, is what we call a covalent molecule. What the chemist Gilbert Lewis found was that in order for these covalent molecules to exist, they have to follow this rule that's called the octet rule. For these molecules to be stable, they need to have 8 electrons each on their outermost shell. So for example, like in this drawing, you can see that atom A has 8 valence electrons. They're not drawing any of the core electrons here, they're just showing the valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And then B can also say that it has 8. 1, 2, 3, 4, 5, 6, 7, 8. The word octet means 8, and you notice that they all have 8 electrons. Now, you might wonder, why is 8 a magic number here? Well, 8 corresponds to the noble gases, and noble gases we know are elements that don't really react with other elements. They're what we call inert elements. So as a result, in molecules, they follow that same rule, and Lewis discovered this concept. So for example, if you look at something like HCl and you look at their valence electrons, hydrogen has 1 valence electron. How do I know that hydrogen has 1? You know, I go to the periodic table, I look at hydrogen. Hydrogen is in group 1, so it has 1. And then chlorine, group 7, has 7 valence electrons. So the drawing looks like this. So then the question becomes, how do these two things combine together so that they're both stable? Well, they can do it by sharing those valence electrons. So if they share, the chlorine now has 8 electrons. You can count them. That means that it satisfies the octet rule. And then hydrogen has 2. Well, it doesn't have 8 because hydrogen is the smallest element, and again, so it only needs 2 electrons to be stable. Hydrogen is the only element that has that property. Everybody else needs 8, okay? We can then draw these type of diagrams called Lewis structures to show how covalent bond forms in a molecule. And the way we do this is pretty much we follow these steps that I've listed here. You start by counting the total of valence electrons you have from all the atoms, and then you have to arrange these electrons as pairs. And then you want to draw a molecule where all the electrons are drawn where each atom has 8 electrons and hydrogen has 2. So this means you have to satisfy the octet rule. Okay, that's a requirement because that's what we see in nature. You can't use more electrons than what you have. You can't use fewer electrons, so everything has to be exactly what you have. So if you count that you have 20 electrons total, you're going to need to use all 20 electrons, okay? And electrons can be drawn many different ways. The ones that we're going to list here are the ones that you'll see in the type of Lewis drawing in this class. There are some electrons that are not shared. In other words, they're belonging to the specific atom. We call these lone pairs. There are electrons that are shared, but just one pair, so we call that a single bond or single covalent bond. If you're sharing 2 pairs of electrons, then we call that a double bond or double covalent bond. And then when sharing 3 pairs, we call it a triple covalent bond. If you, for some reason, can't satisfy the octet rule with the lone pairs and single bonds, you're going to have to start making double and triple bonds to help you satisfy the octet rule. Okay, so we're going to do a few examples of drawing Lewis structure, and the steps that you want to follow is shown on the left screen there. I'm going to do a few of these examples that are given here. So let's start with HBr. When you're doing this, you want to have your periodic table handy so you can take a look at the elements and figure out which group they are found in. Because the first step is always calculating the number of valence electrons in the molecule itself. So in this case, we would look up the periodic table and found that for hydrogen, we have 1 valence electron. And then bromine, they're in group 7, has 7 valence electrons. So the total valence electron is 8. The next step here is to arrange the valence electron as pairs and then draw a structure structure such that the hydrogen has 2 electrons and the rest of the atoms satisfy the octet rule by having 8 electrons. Hydrogen has 1, bromine has 7, and we use these dots to represent the electron. So the question is, how do we combine them so that bromine has 8 and hydrogen has 2? Well, easy. We just bring them together. So the structure would look something like this, right? And so now I can say that my bromine has 8 electrons and then my hydrogen has 2 electrons. And that's exactly what I'm looking for. Typically, a bond is illustrated using a line. And so that's the correct Lewis structure for HBr. That's a single bond. These 3 here are what we call lone pairs. They are electron pairs that are located on a specific atom. Okay, let's take a look at Br2. So step 1, what is the number of valence electron? They're both in group 7, so you have 2 times 7, which is 14 electrons. So each Br is this. Here's another Br. You can see that the thing that makes the most sense is just share those single electrons. So this Br can claim 8 electrons, and the left Br can also claim 8 electrons. We would just do it as a single bond between the 2 Br. In this molecule, there's 1 single bond. There are 6 pairs of lone pairs there. Now let's take a look at the 2 molecules that are of interest to us. Oxygen, valence electron is group 6, so there is 2 times 6, which is 12 electrons. When you draw it out, it's 6 on each side. Here's another oxygen, 6 on each side. This becomes a little difficult. How do I draw it so that both atoms have octet? If you put them together, this is what it's going to look like. Okay, so notice that the right oxygen can claim 8 electrons, and then the left oxygen can also claim 8 electrons. So they both satisfy the octet rule. So what does it look like? So there's actually 2 bonds there. And so that's what we call a double bond. And a double bond, as you might imagine, is stronger than a single bond. It's harder to break because there's 2 of them connected together. Just like if you put 2 pieces of rope to tie together versus just 1, it's a lot easier to cut 1 versus 2. Now let's take a look at the next molecule, which is ozone. Ozone has 3 oxygen, group 6, but now there's 3 of them, so 3 times 6 is 18 electrons. Another way to do these Lewis structure drawing is with single bonds first and then figuring out how to place the rest of the electrons. So for example, if I have ozone here, I know that I'm going to connect them this way first, okay? If I connect them this way, that tells me that I've used up 4 electrons because each of those single bonds is a pair of electrons. So I'm going to subtract out 4 electrons since I used them up already, and I'm left with 14 electrons that I can use in such a way that everybody satisfies octet. So how am I going to do that? It's a trial and error process, so I would just go ahead with putting 8 for each of the outer oxygen. That would mean that that oxygen has 8. I've used 6 electrons there, so minus 6 here, that leaves me with 8 electrons. And then I'm going to put another 8 for this other oxygen. That's another 6 that I use, so 2 electrons left. The only possibility to put those 2 electrons is right here in the middle. So now I've used up all my electrons. Again, I can't use more or fewer electrons than I have. I have to use exactly the correct number of electrons that I have. Does everybody have octet? If they don't, then I have to fix it because there's a problem with the structure. So if I'm looking here, I see that this one has octet on the left, this one has octet on the right, but the one in the center doesn't have octet because it only has 6 electrons. So 1, 2, and 3. How do I draw this so that I get octet for that center one without really affecting the other guys? So the way you do this is usually by taking one of the lone pairs and making them a double bond. So you can, for example, take this lone pair right here and put them here to make it a double bond, or you can take one of the outer lone pairs and put them here and make them a double bond. Think through this a little bit, but you'll find that the only possibility that works that will give everybody octet is to take one of the outer lone pairs. So you can draw it this way. So if I take that green one that I just drew and make it a double bond instead, that means the center one's still left with its own lone pair. The left side has that structure. Okay, so the right oxygen has 8 electrons, so that satisfies octet. The left oxygen has 8 electrons, that also satisfies octet. The middle oxygen also has 8 electrons, so it also satisfies octet. So everybody is happy at this point, so that would be a reasonable structure of ozone. You don't necessarily need to have the double bond coming on the right side of the molecule. You can also have the double bond coming on the left side. So if you do it this way, it still works. So which structure do you have to pick? They're actually different structures. You might think that I'm just rotating one into the other one, but no, you can actually use different isotopes of oxygen, and you'll find that there's ways to label these oxygens to make them unique from each other. There's really no preference to
to the left or to the right. So what we do is we put this double-headed arrow to indicate that either structure works. But what's surprising is that neither one is the real structure. When I say real, I mean the thing that we actually can see when we do an experiment and take a look at the structure of ozone. It turns out that it looks like this. So it has a single bond, and then it has additional bond on the top, but not quite a double bond. So in fact, it's like taking this whole thing here and averaging them out, okay? So average structure. So if I look at this bond right here, on the right side, I have a double plus a single, so 2 plus 1 is 3. 3 divided by 2 is 1.5, and that's exactly what this bond is. It's a 1.5 bond. Same thing on the other side, I can add 1 and 2, get me 3. 3 divided by 2, since I'm averaging over 2 structure, it gives me 1.5 here as well. So ozone has 1.5 bond. In reality, it does have bond that is slightly stronger than a single bond, but slightly weaker than a double bond. And this structure actually matters a lot, as you'll see in the next lecture, on why ozone absorbs UV radiation of a certain wavelength compared to oxygen.